All right, welcome to video 2 of part 2 of our lecture video series for Friday, May 12th. We just looked at the effect of molecular size or mass alone on the vapor pressure and boiling point of a particular substance. And now we're going to add on to our understanding of physical properties like vapor pressure, boiling point, and then further down the line, melting point of a substance by using what we know about intermolecular forces. So we left off by asking ourselves this question, which was, what happens to our trends in vapor pressure and boiling point when we take into consideration that all of these molecules in each of these samples are interacting with one another, meaning there's some degree or type of attraction or repulsion that's happening that is going to affect what's going on with this vaporization process. So let's start by making a statement that I think we could all agree is one that follows kind of common consent, can I speak today? Common convention or common sense. So in general, the stronger and higher degree of the intermolecular forces in a substance, the more energy is required to overcome those forces and cause some kind of change in phase. So stronger intermolecular forces requires more energy. So for example, let's consider the case where we have, let's say, NH3, ammonia, versus something like, let's do, what do I want to do? How about CH4? All right, so what is the difference between ammonia and methane? So in ammonia, this is a polar molecule, and in particular, it's a polar molecule whose dipoles are really strong because we have bonds between a highly electronegative molecule, a highly electronegative atom like nitrogen, oxygen, or fluorine, bonded to a very weakly electronegative atom, the hydrogen atom. So here we have hydrogen bonding, which is a type of dipole-dipole intermolecular force that is incredibly strong. Now compare this to methane. Methane, this is a nonpolar compound, right? It has this tetrahedral geometry and no lone pairs. So we have this equal and opposite pulling on our shared covalent electrons as a result of the electronegativity difference between carbon and hydrogen. But even then, the difference in electronegativity between carbon and hydrogen in the first place was relatively small. So overall, this is a nonpolar molecule. Now, as we recall from Wednesday's lecture, nonpolar substances don't not interact, right? Like there is still some kind of degree of intermolecular interaction that exists between nonpolar molecules. Like it's not just molecules that have these dipole moments that are always fixed that interact with one another or stick to one another or repel one another. It happens with these nonpolar compounds too. And the way that this happens, remember, is through the idea of an induced or instantaneous dipole. So recall what's going on in a substance at all is we've got this molecular orbital that has a distribution of electrons in these orbitals. And remember, these orbitals are probability maps, right? They tell us where we are most likely to find an electron. So statistically, naturally, there's kind of some variance in where our electron is likely to be found within our molecular orbital. So sometimes we might have electron density that is clustered around one end of the molecule. That creates a momentary, very small little baby dipole moment, which then affects kind of in a cascading or domino effect any surrounding molecules to have an induced or momentary dipole. And because those little momentary dipoles are in fact dipoles, they are going to attract and repel one another, albeit through these kind of weak little means. This is what we call dispersion or London dispersion forces. And again, this is a result of just like natural fluctuations in electron density around our compound, creating these little momentary, short-lived, and very weak dipole moments. So let's think about what might happen to the vapor pressure of the ammonia compound compared to the methane compound. So because this has hydrogen bonding, right, there's a lot of intermolecular forces that exist between each ammonia atom. So when we think about the amount of energy that is going to be required to put everything into the vapor phase, we have to overcome the stickiness of this molecule to itself. So it's kind of like, imagine that you are standing in the front of a room and there's like 20 people between you and the back of the room. If you had to make your way to the back of the room without interacting with anybody, you could probably find yourself statistically reaching the back of the room more easily, right? Because you wouldn't have to interact, touch, or talk to, or get caught up in anybody else that's in front of you. However, let's say that you were at the front of the room and there were 20 people in front of you and you were trying to get to the back of the room, but you had to give everyone in the room a handshake before you could move on to the back. You are now caught up in a bunch of intermolecular forces between yourself and the other people in the room, meaning it is going to be less likely for you to reach the back of the room. What does that translate to here? Well, if I'm a molecule that is wrapped up in being attracted and repelled by my neighboring molecules, then yes, I might eventually venture my way toward that liquid gaseous boundary, but then some intermolecular force is going to tie me back in. So it's going to decrease the overall statistical likelihood that a molecule makes it to that gaseous liquid boundary and then escapes up into the vapor phase. The molecules are so wrapped up in one another that it's harder for them to escape into the vapor phase. So because ammonia has a high degree of intermolecular forces, we've got those strong dipole-dipole interactions that we call hydrogen bonding, we would expect to see a lower vapor pressure, which means that our boiling point is going to be higher. We have to overcome those attractions between our molecules by adding more heat to the system. Think of it like if you were able to sprint your way through giving everybody a handshake in that room because you had more kinetic energy, because someone gave you thermal energy, then you'd be able to make it to the back of the room a little bit more. Now compare that to something like methane where we have London dispersion forces. So we have these kind of really weak little momentary interactions. This is not something like having to give everybody a handshake, but rather having to at least like bump somebody on the shoulder as you move. So yes, you're going to be interacting with people as you move from the front of the room through the back, but that interaction is not going to keep you strongly tied up with or interacting or nearby all the other people, right? The molecules themselves are going to have these kind of brief, momentary little attractions or repulsions, but then they kind of get over it, right? They can freely free themselves literally from those electrostatic forces. So for a molecule like CH4, we would expect to see a higher vapor pressure, certainly compared to ammonia, meaning we would then expect to see a boiling point that is lower. Now, this is looking at just intermolecular forces, so this is thinking about from only the perspective of intermolecular forces, like if that's the only thing that would affect our vapor pressure and our temperature, our boiling point. So let's go ahead and do ourselves a favor and look at the molar mass of each of these compounds. So ammonia, NH3, has a molar mass of 17.031 grams per mole. And then let's see here, methane, molar mass, 16.04 grams per mole. Okay, now that we've got this molar mass or molecular size accounting, we've just further demonstrated this trend, right? This is heavier and this is lighter. So if I were to try to compare their vapor pressures and their boiling points, I would see the same trend as I would with my intermolecular forces. So these kind of compound on one another. So only if size is considered, but then if you put these together, we have kind of this definite result of ammonia having a lower vapor pressure and a higher boiling point, and methane having a higher vapor pressure and thus a lower boiling point, by considering both the overall molecular shape or mass and the type of intermolecular forces that are present. Now, sometimes it's going to kind of be a toss-up. You have to weigh your degree of intermolecular forces against your overall molecular size to figure out what your trend in vapor pressure and boiling point might be. Also, I know that I said this is something that we might talk about, which was melting point. So the melting point trend is also the same. So the more intermolecular forces that we have in general, we are going to need to increase the system's thermal energy in order to overcome those intermolecular forces to cause a phase change. So these all kind of trend in the same direction. Okay. So you will practice this a lot on active chem. Again, this is going to come back in OChem, but in general, this is kind of an overview of how molecular mass, shape, and also intermolecular forces affect physical properties like boiling point, melting point, vapor pressure of different compounds at some particular, no, just of different compounds. Okay. So now let's move on to part 3. So we are now firmly looking not at just general compounds, but in part 3, we are moving on to our conversation about liquids. So we've had a conversation about the gaseous phase, right? We've talked about the ideal gas law. We looked at how we describe phase changes and the kind of thermodynamics of phase changes. And now we can finally talk about the other phases. So we've got liquid and solid left. So let's start talking about liquids. So we're going to look next at intermolecular forces and how they manifest in physical properties of liquids, specifically looking at the physical properties known as viscosity, surface tension, and capillary action.